Welcome to Radar System course. Today we start here a Omega navigation system. So Omega navigation system, it is used in a worldwide for the radio navigation system, and it operates in the very low frequency. So that very low frequency operate in between the 10 kilohertz and a 14 kilohertz there, and it provides an all weather navigation service to the marine navigator. And the system consists of a 8 widely spaced transmitter, and these transmitting stations, these are the transmitting stations we have written here A to H here. These are the various transmitting station and their operating frequencies, and these are all the 8 transmitting stations. They are operating in between the 10 and a 14 kilohertz of frequencies, and out of this 8 station there is no master or a secondary relationship between the stations there. And the navigator or a marine user, they can receive the signal from any pair of station, and from the pair of station signal received by the marine receiver, and from that they can find out their locations there. Okay, so means in a Lorentz system there is a transmitter and receiving station there, and in Lorentz they are using a time delays between the signals there at a reception, and that time delay is useful for finding out the location. But in the Omega, they measure the phase differences between these two signals, and from this difference they can find out the what will be the allocation. So each Omega transmitting station transmit the frequencies. So in between that, a 10 to 10 kilohertz to 14 kilohertz. So for example, we say that in Norway here we say that it is about a frequency of a 12.1 kilohertz. So if you see the transmission format for this, so it transmits a signal frequencies from 10.2 kilohertz to the 12.1 kilo. So that is about a frequencies by the each transmitting station. So we have mentioned that a frequency reference here, but common frequencies for this particular transmitting station, they are a 10.2. These are about the common frequency station frequencies, 10.2 kilohertz, then 11.05 kilohertz, then 11.3 kilohertz, and then 13.6 kilohertz. Okay, so now these are about the a common frequency signal to be transmitted by this a transmitting station. So means each omega transmitting station. So these are about the Norway. They are operating at 12.1 kilohertz frequency, but they can transmit the signal of frequencies of what? A 10.2, 13.6, 11.3, 11.0. Okay, so means they have the total, if you consider that 8 transmitting stations. So each transmitting station, we say that they following the a band of a frequency. Okay, these are about the frequency range here. They are using them, and then we consider that supposed to be in Norway here. So we can consider the band of a frequency. So just remember this particular band of frequencies. Now for this a band of a frequency, for example, we can say that this one is about a 1, then 2, 3, 4, 5, 6, 7, and 8. Okay, now these are about the a band of frequency. So for the Norway, we can consider that 10.2, 13.6, 11.3, okay, likewise 12.1, 11.05, and 12.1. Okay, so likewise we can have a band of frequencies there that is to be used by this Norway. So likewise, so we have the different band of frequencies. So we supposed to consider this 4 frequencies there, 4 unique frequencies for this each and every station. That is about a transmitting station there. And every transmitting station they have some particular interval time interval transmission interval for each and every station there. So these two stations they will not transmit the same frequency at the same time. Okay, I mean suppose I am saying that in Norway is transmitting at 10.2, so this another station will not transmit the 10.2 signal frequency at the same time. Okay, they will transmit in the given particular band of frequency at a time one. So there all the station transmit at different frequencies. So suppose I am saying that 10.2, so this will transmit a 12.0. Okay, so 11.3 here. Okay, so 11.05. Okay, so likewise, so we can consider that a 12.3, 12.5, 11.10, 12.6. Okay, likewise. So these are about the various frequencies transmitted by this particular station. So each transmitting station, if you consider that, so they have the different transmitting frequencies at the particular period of a time. So means no two stations transmit the same frequency at the same time. Okay, so that is to be important here. And each transmission segment is between zero point 0.9 second, that is about a means we can say that the transmitting signal is about a zero point 0.9 second, means that is about a transmitting time that is about a zero point 0.9 second, a long here, and 1.2 second a long here. Okay, that is about a transmission. And then in between that each and every transmitting station there will be a zero point 0.2 second of a interval. Okay, so means we can say that a transmitting station band. Okay, so we can say that this is about transmitting, and this one is about the interval between these two stations. Okay, so like that. So this one is about a zero point 0.1, zero point 0.9 long or a 1.2 long, but in between that two, there is a interval between these two band is about a 0.28 seconds of a duration. So each station continuously repeat the its transmission cycles here, and then at a receiver determine the position from either a direct ranging mode or the hyperbolic mode here. So some cell transmit. Okay, some we can sometimes we can say that at a receiver we suppose to be consider that a direct range mode or a hyperbolic mode. So in that case, in the direct ranging mode, the receiver measure the range from the station. Okay, there are the two different modes. One is called as a direct ranging mode. Okay, and another is called as a we can have hyperbolic mode. So hyperbolic mode we have seen earlier, that is in a low run. So that is they form a line of point based on the particular signal frequencies there. And in a direct ranging mode, they receive the signal or receive the signal and measure the ranges from the stations there by measuring the phase shift between the transmitted signal and an internal reference signal. Okay, but in the case of a hyperbolic mode, the receiver measures the position relative to the transmitter pairs by making the phase comparison between the signals coming from this particular pairs there. Okay, so means they forms the pair, and according to that they will change their position. Okay, so in the case of a direct ranging mode, we can consider that operating frequency is omega wavelength at a 10.2 kilohertz, and it is we can say that approximately is about a 60 miles long. Okay, that is about a omega wavelength. Omega wavelength at 10.2 kilohertz, and it's about a 16-mile long, and that wavelength defines the width of each omega lane. Omega lane means what? For a particular signal of a frequency. Okay, suppose I say that we have a particular signal is to be transmitted here. In that case, we supposed to consider that one cycle of a lane. So this is nothing but a one cycle of lane, another cycle of lane. So likewise, so this one is called as a one cycle lane. Okay, one cycle lane, not length. Okay, so from this we can consider that a signal is to be transmitted by this. So this one is about one lane. Okay, and this one, for a given particular signal there will be the amplitude, but in the case of how they formed a lane here. Okay, so they form the lane with a line of point. Okay, this one, so supposed to be, here is your a receiver now. Okay, so I supposed to draw in a different way here, and this one is about a transmitter transmit. So from this one is, sorry, this one is about a line. From this we can say that this one is about a one lane, this one is about another lane, this one is about another lane, so likewise. So we can say that this one is one lane, this one is a second lane, this one is about a third lane. Okay, so like, so means this particular lane is corresponding to this one. Okay, so likewise. Then a two lane. So likewise we have a different lane. So if you consider that we have the different lanes there. Okay, this way we have a different lane, and that particular lane based on the what will be the a cycle of the a transmitting signal. So we found here at a particular transmitting station from this particular, there will be the a circle, or there will be the concentric circle, or there a line of line there, and then a omega receiver measures the phase of the received signal with a known lane. So whichever the lane is there, and that particular phase shift is useful to determine its position. Okay, uh, in between the whatever the distance between the a lanes here. So for that purpose, it should know that which lane that will provide the distance between the, what will be the distance between the particular lane there. Okay, so what particular lane is to be transmitting there, and what will be the lane boundaries. Based on the lane boundary, that receiver will calculate the what will be the line of point there. Okay, and that line of point is useful for the what will be the distance between the lanes, that will be calculated by the receiver there. Means transmitting the station, we can, they form a lane there, so that called as a omega lane, and that omega lane are not stationary there. So based on that how the signal is to be transmitted there, so according to that it changes there. So we have some particular reference signals for this omega there. So from this omega signal from the receiver, so it will compare from the transmitting station and their reference signal, and according to that they will find out the what will be the a positions in a plane there, or what will be the locations. So if we consider that a two transmitting okay, their stations now, so we need to consider that here is a one station. Okay, so they forms their concentric circle now. Okay, so likewise you can consider that these are the circles formed by this particular station. Okay, that is about a transmitting station. Then another station is here. We supposed to consider that another station here. They form their concentric circles likewise. Okay, so likewise they form their concentric circle. And at a some particular point, if supposed to be observer, okay, or we can say that a omega receiver. Suppose omega receiver is present right now. Okay, so that is about a receiver, omega receiver. And these are about the two transmitting station A. This one is about a B now. So then from this we need to find out, okay, what will be the distance. So distance between what, that particular point. Okay, so this one. So this one is a distance, and this one is about a distance. That is about a direct range. Okay, so that is about, that is called as a direct ranging mode. And that direct ranging mode, they will fix their position. Okay, So that's what this particular point. Suppose at a receiver is supposed to be at one point here. Then at this particular lane, the distance between the lane boundaries, whatever we have, and from this information, the receiver will calculate the distance between the this to this and this to this here. Okay. Suppose there will be the another receiver at any point. Then they will calculate the distance. So according to that, A and B, okay, distance between this particular will use here. Okay. And then that particular distance, okay, is used to determine the what will be the distance between the lane boundaries at a given particular 2 point. Okay, so that will be useful. That is this is called as a direct ranging mode. Then next about a hyperbolic mode. In a hyperbolic mode, these are about a transmitting station. We supposed to say that these are about the concentric circle for this particular station, and then they have the central line for the given particular transmitting station, and another station here. Okay, now these are about the base station, and then this one is nothing but the base line from this two station. Okay, this one is about a base line, and from this we need to find out a distance here. So direct in a direct range mode, the receiver measure the distance between this particular transmitting station, and from this distance they can find out the what will be the their position there. In hyperbolic mode here, the receiver measure the difference in the phase between the two transmitters. Suppose at the particular position is the okay. So according to that, they will receive the signal, and from this particular received signal, they will find out what will be the position. Now these are about the two transmitting stations. For example, we consider that. Okay, and then transmitting station transmit a wave. Okay, whatever the wave is transmitting, it has a zero phase at a given particular period of a time. So means we can say that if phase is zero at each wave front, this one is nothing but a wave front there. Okay, so means at each every repeated interval time there is a zero phase, and the phase difference, okay, where we are getting at the wave front, if intersect at that particular period of at a particular time, and that particular phase difference that will be useful for calculating the positions there. Okay, so that's all about a omega. So the receiver in a direct range mode measures the ranges from the station, and it is done by measuring the phase shift between the transmitted and a reference signals there. On the other hand, we have considered that a hyperbolic mode, it measures the position relative to the transmitter pairs. Okay, so according to that, these are useful for the what will be the locations. If you consider here omega, so that will be useful. That will be that uses a lens there and a phase comparison at a difference frequencies there. Okay, and in this one omega, it doesn't require any master station there. Okay, all the stations transmit the signal, and a receiver navigator will use this a two station or whichever the station, and from this they can find out their location. That's all about a omega here. So next we will consider that another system that is called as a DECCA navigation system. We'll see that another navigation system that will be a DECCA navigation system. Okay, and this DECCA navigation system, again it is called as a hyperbolic electronic navigation system. So just like we have seen earlier a line of point on. So similarly this one is about a DECCA LoRa. So we have seen that hyperbolic line of point. So similarly here a DECCA is again a hyperbolic electronic navigation system. And this navigation system was first used in a World War 1944 here, and it is basically a range difference system. Its range differences are interpreted in a phase differences here, and A line of phase differences are in the form of a hyperbolic with a foci at their a transmitter there. And it consists of what? A master and a slave. Okay, so we have considered earlier that is a master and a secondary. It has a master and slave there. Okay, in a Loran master and secondary there, but here it has a master and slave is there. Okay, and it consists of a master. So means each station they can be any station can be one of the master and another is the slave, or they can operate for a given particular receiver master or a slave at a particular time. Means distributions of a master and slave is depends upon the what will be the chain of a DECCA. Generally, a DECCA chain consists of a master station controlling the phase of a another slaves there. Okay, so means it has just like a chain of a master and slave. Okay, so suppose we can consider that there are the four stations now. Okay, so we can say that it has a one master and a three slaves there. So means they have the chain of a master station controlling their phases of these three particular slaves, and they are situated 110 120 degree apart. Okay, so all these stations they are situated about 120 degree apart at a radius of a 60 to 100 miles. 60 to 100 miles from the a master zone, and that will provide the all round coverage, and they use a frequency signal. Okay, so means operating frequency is about a 70 kilohertz to the 130 kilohertz frequency band. Okay, so because we can consider that they cover the all the coverage because the signals are passing from the different lanes there, so that's why the coverage area will be a larger there. So each station in the chain, okay, they just consider one transmitter, and that normally transmit a particular unmodulated phase stable carrier wave, and this carrier were all harmonically related to an internal station references there, and they are about the frequencies. Reference frequency is about a 14.2 kilohertz. So that is about a reference frequency, that is about a generating frequency. So if we consider the master there, so master is one of the six. Okay, so we consider here the master slave combination there. So in that case, a master station normally transmitting its frequency signal. For example, we consider that if F is a transmitting frequency signal, and that is a reference frequency signal is about F is about a 14.2 kilohertz. Okay, so master station, we have a station that will transmitting the signal is about what 6 into F. Okay, so in terms of a carrier wave signal, so 6 into 14.2 kilohertz, that will gives you the 85 kilohertz of a band, and a slave station that is called as a RAID. Okay, so we can say that a RAID slave station. Okay, so that RAID slave station, and that will transmitting the signal of a 8F, and that will be in the band of a 112 kilohertz band. Then another slave there, that is about a green slave there, and they are transmitting the signal frequency is about a 9F here, and it is about a 127 kilohertz of a band here. Then a purple slave that will be of a 5F signal, and their band of frequency is about a 71 kilohertz. Miss slave stations and a master station, so they have a combination. Means if you consider that they are just find out the differences. Okay, so means differences of this receive signal. Means slave station received a signal from this master, okay, reference signal, okay, and from this, so they are operating. So if you consider that the operating range of frequencies for the master slave there, so we say generally it is about a 6 7. So range of a frequency for this, it will be what, 84 to 86 kilohertz, okay, 86 to 80, 86 kilohertz. So similarly we have a frequency range is about a 112 to 115 kilohertz for this green here, 126 to 129 kilohertz, and for this 70 to 72 kilohertz. So this signal is what, a continuous signal, okay, and the signal is transmitting, so it has a spacing of a 150 hertz. So sufficient spacing, because of that sufficient spacing there won't be any interference between the stations there, okay, and this signal will be transmitted by the transmission, okay, these are the transmitted, and that will be received by the receiver, and then from this receiver they just multiply, they have the multiplying circuit and they produces their phase comparison of this particular signal. So after that multiplier they are getting that a signal from this master red, then master green, okay, and then master purple here. So if you compare here, they are getting that 24F for the master and a red, then a 18F for master and a green here, then a 30F for the master and a purple. So now that's about a multiplier. If you see the architecture of this particular a DECCA here, so it has a multiplier, it has a master stations and all. So for example, we consider here, let's take a this thing here. In that case, we need to find out, okay, that's about a DECCA here, and they have the a reference signal, that is about a reference pulse source. Okay, so we can consider that about a reference pulse source, that is about what is used for the master, or we can say that, okay. So generally for the master is about a 6F here. So generally we consider that is about a 1F right now initially, and then it has a slave of what, okay, so we can consider that about a that is a slave of what, if it is a green, a red, it is about 8F, if it is a green it is about a 9F. So similarly we have a different signal frequency. So for the master and for this red and purple it will be different here. So 5F for purple, then 6F master, then 8F we have a radio, then a 9F for green. Now then it will be multiplied. We can consider that about a whatever the receiver signal received. Okay, so these are DECA receive. So they are receiving the signal. 6 multiplier we have, and then we have a master and slave process. Whatever the signals we are getting, that will be multiplied, and the difference in the page from this master and a purple, master and a slave, master and red, master and a green. And that will be obtained, and that particular difference is useful to find out what will be the uh, positions now. Okay, so on that will be seen on the a decometer. The output of this particular frequency multiplier here, we have x6 here, that will be applied to the discriminator. Here is we have a discriminator now. This one is about a 30F discriminator now, and that will be given to the, because we have the master. So for the master, it has a different multiplier. So 5, then a 4, then a 3. Okay, and then that will be useful to obtain the, what will be the purple one. Okay, signal. And these are called as a decometer. This one is about a decometer. So similarly, for this red here, okay, so we can consider that a 24 discriminator from this red, okay, red to 3x, we consider that a multiplier here, and from this, then it will be about a red decometer. Then a green, that will about a multiplier 2 here, and after that 18F discriminator, then we are getting that is about a green here. Okay, this will be seen on the a decometer. So how this decometers look like means we have a hyper, because it is about a line of point. Okay, hyperbolic line of point. So transmitting station, one master station transmit the signal, and at a observer point they have this different decometer, that is purple, red and a green, and from this they observe the a positions there. Okay, means we can consider that they have the different frequencies, okay, for this red, green, purple as well as the masters there, and then they would measure the phase differences, and that phase differences are displayed on the decometer. So means purple, red, green, these are nothing but a phase meters, and they find out the differences there. Okay, but somewhere at some particular areas there may be the zero difference there, and that zero differences, these are the lines, and that lines are called as a lanes. Well, generally we have seen earlier a signal, so we can consider that about it, what will be the aliens here, like that. So what about the aliens here? Means there whatever the difference present at the particular point, and that is called as a aliens here. And then we can see that how it operates. Okay, so these are nothing but a decometer. So one of the masters we say, okay, they have the hyperbolic lines we have. Okay, so another master we say, they have their hyperbolic lines there. So similarly, it has the slaves. Likewise, they have another slave. Okay, so like that about the hyperbolic. So from this, we need to find out the position. Suppose a position at a receiver. Okay, means we have phase comparator in between the a at this particular receiver, and then they find out the phase differences between these two particular frequencies. Okay, so we are getting the accurate values of this particular position based on the a phase differences. So and we have seen that they have the multiplier. Okay, but generally if you consider that they are transmitting a pulse, and that each and every pulse they have some particular lane there. Already we have seen that this one is about a pulse now. So this one is about one lane, two lane. Likewise, so we can consider that at that particular lane there will be the a zero difference there. Pulse transmitted by the station, okay, within a particular period of a time there, and then they will find out the what will be the a difference at this particular period of a time there. Okay, so that's about a decometer here. So we will consider that how this decometer looks like or supposed to be in a particular region. So how this decometer is to be used here. Suppose it has a master station now, and here we have a slave station. So what happened here? A master transmits the signal. These are about the hyperbolic lines of the master station, and then these are about the for the slave. These are about the line of points of this hyperbolic station. And supposed to be at somewhere place, suppose there is observed, okay, this is about a receiver now at this particular point. The receiver find out the difference here from these two signals, and from this they will find out the what will be the phase difference. So means there are multiple stations, okay, chain of stations are there. So transmission from the chain of station that will be received by the receiver here, and that will measure the differences in the phase of a signal, and that will be arriving from the master and a slave there. So means all the stations or all the chain of a station, they must have a phase log so that they can find out the a distance properly. And these master and a slave stations, they are 100 nautical miles apart from each and every station there, and that phase difference that will be determined to useful for the a distance there. Each slave station they are fitting with their information regarding the master signals. Okay, means slave stations receive the signal from the master station, and then it will convert into the slave frequency, and that will be useful to control the oscillators of the slave transmitter there. So that's why a constant phase relationship is maintained in between the transmitter, master transmission, as well as a slave here, and that will be useful to find out the that will be useful to opt at a receiver accurate position of a lane and everything there. Okay, so every station is to be checked every time what will be the positions, what will be the phase and all. And it generally a decometer. So DECCA navigation system they are using a decometer, and that decometer they are detecting the phase differences, and they are displaying their phase differences on a phase meters that is called as a decometer, and the readings that may be plotted on the DECCA lattice chart in terms of a line of positions, and that are useful to find out the door location. So how that decometer will be looks like. So generally if you consider that this one is about a red now, and they have the positions there, and then they have some particular meter, okay, they have some particular meter, and they just find out from what will be the position at the particular scale there. Okay, they can be used as vernier scales also, but here is supposed to be it will start from the one one two, this one is about it zero here. Okay, so likewise, so up to that we have the a9 here. So similarly outer meter has a 24 lines there, and then they will find out what will be the position. So reference is there where we are getting the zero difference, so that's why a zero is mentioned on this meter, then a reset is mentioned there at this particular point, and then they can find out what will be the phase difference. So that is about a test. Okay, so likewise there will be the green decometer, purple decometer that will be the available on the a ship there. Okay, or a marine there. Okay, so that will be useful for the navigation system. So they provide a higher degree of accuracy because of the continuous transmission, and then they have the if phase differences. Okay, they can be useful for calculating the whatever the locations are. With this, we stop here, and we have seen that in navigational aid, what are the fundamentals of a navigation aids there that we have seen, and in which we have seen a various navigation systems. With this, we stop here. So thank you all.